What is quantum entanglement? Part 1 by YKademy. Hey guys, this video is part 1 of a 2-part series on quantum entanglement. Once you're done, be sure to check out part 2. You may have heard of the famous phenomenon that Einstein referred to as spooky action at a distance. In this phenomenon, entangled particles remain connected, so that actions performed on one affect the other, even when separated by great distances. To understand this concept, let us first look at a non-quantum version of entanglement first. Entanglement arises in situations where you have partial knowledge of the state of two systems. For example, our systems can be two objects that in this scenario we represent as apples. Our apples come in two shapes, square or circular. These are its possible states. Then the four possible joint states for two apples are circle circle, square circle, circle square, and square square. This table shows the possible states and the probability of being in that state. We say the apples are independent if the knowledge of one state does not give information about the state of the other. What does this mean? Let's take two apples and place them in two different boxes. We open the first one and see that the first apple is a square. However, we have no idea what is the shape of the apple in the second box, as the two apples are independent of each other. Our first table has this property. If the first apple is a square, we're still in the dark about the shape of the second. The same scenario occurs for the second apple. On the other hand, we can say our two apples are entangled, when information about one improves our knowledge of the other. Our second table demonstrates entanglement. In that case, whenever the first apple is circular, we know the second apple is circular too. Let's represent this with our two boxes example once again, though this time instead of ordinary apples, we'll use entangled ones. We open the first box and see that it is square. We immediately know that the second apple is a square too, as the apples are entangled. Knowing the shape of one, we can infer the shape of the other. This non-quantum phenomenon is known as classical correlation. The quantum version of entanglement also has a lack of independence. In quantum theory, states are described by mathematical objects called wave functions. The rules connecting wave functions to physical probabilities introduce interesting results, but the concept discussed carries over. However, in real life, apples don't count as quantum systems, but quantum entanglement arises in nature, for example, in the aftermath of particle collisions. Returning to our example, if you write phi square phi circle for the wave functions describing system 1 in its possible states, and psi square psi circle for the wave functions describing system 2 in its possible states, then the overall states will result in these equations, which are the mathematical forms of what we talked about. Quantum entanglement has an aspect called complementarity, which makes it different from classical entanglement. Previously, our apples could only exhibit two shapes, square and circle. Now let's imagine it can also exhibit two colors, red and blue. This adds two more possible states. For classical systems, this added property would imply that our apples could be in any of four possible states: a red square, a red circle, a blue square, and a blue circle. Yet, for a quantum apple, a quapple perhaps, the situation is different. The fact that a quapple can exhibit different shapes or different colors does not necessarily mean we can observe both aspects simultaneously. Why, you may ask? To understand, let's take a different example. Physical objects can be expressed as both waves and particles, which we'll use for our example. Though while objects are both a wave and particle at once, we can't observe them both at the same time. It's similar to how you cannot turn your head left and right at the same time. Depending on the nature of the measurement, the nature of the property shown is determined. Using our previous analogy, depending on which direction you look at, the direction your head turns is different. We can measure the shape of our quapple, but in doing so, we lose all information about its color, or vice versa. Each view offers valid but partial insight. This is the heart of complementarity, as Niels Bohr formulated it. Quantum entanglement is a phenomenon where the state of particles cannot be described independently, and the measurement of the particles are correlated. We will go into more of its unique aspects in the next video. That's all for this video, guys. Be sure to check out part 2. Hope you all enjoyed, and don't forget to like, comment, and subscribe.